Hi, everybody. This is Nalini Elkins with Industry Network Technology Council. I hope you can all hear me okay. If somebody could send me a quick note, that would be perfect. We are continuing today with our series on IoT, and this is a part of our bigger series on IPv6 for enterprises. The reason we chose IoT, of course, is because at scale, you probably want to go over to IPv6 for IoT. And that is one of the things Pascal will talk to us about today, is some of the differences when you get to things like neighbor discovery and so forth. So one interesting thing, if you guys would like to, if any of your organizations would like to reach out to us to help us talk to your internet registry or help discuss what size IPv6 address block you want, please feel free to reach out to us. I was on a conference call earlier this week with one of our federal government agencies in the United States who took us up on that offer, and we were able to get them a very nice address space along with Aaron. So please feel free to reach out to us. We'd like to help you. This is a joint effort from the India Internet Engineering Society, which is a nonprofit, and INTC, also a nonprofit. This series of webinars is being funded by ISIF Asia. When this grant will expire at the end of 2022, we will be continuing on with our webinar series. I suspect next time we will also cover security, as all of those things very much impact IPv6 and of course enterprises and everyone. So I'll quickly skip past my bio. It's here if anybody wants it. The really important person here is Pascal, who is a stalwart at the IETF and has been behind many of the developments in IoT at the IETF. He has, of course, many patents. So on that note, I will stop talking and turn it over to Pascal. Thank you so much for your help, Pascal. And as always, this session is recorded.
I'm here, Nalini, and I will start sharing. So, can you hear me and see my slides okay?
Yes, we hear you and see you fine.
Oh, good. So this is a new webinar for the IoT track, and this is basically the faces of the people who have been presenting or preparing this amount of sessions. And you recognize Karsten, you recognize Georgios on the top, and I'm on the top right. So this is effectively the fifth of the original 5 sessions we had prepared. But as Nalini has and will explain again, I guess there will be more sessions and sound, or more precisely traces and stuff that you can look at. Today's session is about 6LoWPAN neighbor discovery and RPL, because they interact, and I will show you how, using a combination of 6LoWPAN neighbor discovery and RPL, we can build subnets of thousands or even tens of thousands of nodes, and we are actually deploying those things in the smart grid. Whereas in the traditional automation network, even on wires, the recommendation is not to have more than 100 nodes. And that's because of the severe limitations and expectations of IPv4 ARP and inherited from ARP IPv6 ND. So we'll go through basically the shortcomings of IPv6 ND to start with, and the models that we have for radios and low power radios, but any radio, And then we'll see why we have defined 6LoWPAN ND, the new method, stateful address to configuration that's used in 6LoWPAN neighbor discovery, and how this interacts with REPL to maintain a very reliable state about every address in the subnet and route it through REPL. And with this, I will start with the classical IP model, which is probably the one you've learned at school and which is fully inherited from v4. So you need to keep in mind that v4 is somehow like 40 years old, v6 is 20 years old. From the perspective of today, they are kind of old, both of them. Second thing is the v6 developer, the inventors of the beginning, they wanted to do something new and something better, but the model they had in mind was the same model as IPv4. The Ethernet was the same. I mean, there were no radios, there were no overlays, there was nothing. And so for a number of things, thinking about it or not, they kind of inherited the exact same designs. And in particular, ND, even if it has new methods like stateless configuration, the basic model of how being reactive and using a broadcast to locate stuff, this is completely inherited from IPv4. So let's look at it in a bit more detail. So the traditional model is that you have a layer 2 network, like a network of switch, and that network will have what we call transitive property, meaning that if A can see B and B can see C, then A can see C. And if you have this transitive property, basically what that means is you have any-to-any connectivity at layer 2. And so you can send a broadcast and say, hey, where are you? And the guy will say, I'm here. So if you need to resolve an IP address into a MAC address, then the broadcast is doable. And with the very old yellow wires, before you even had switches, a unicast or a broadcast would use the copper anyway, so it didn't make any difference in terms of throughput or reliability to send a broadcast or a unicast. So this explains a lot about how IPv4 ARP was designed, being reactive and using broadcast. By being reactive, I mean that when you don't have the mapping of an IP and a MAC, it's okay, you can just ask for it, and then you will build a cache. So think about the adapters of 20, 30 years ago, where you could store only a few entries in your neighbor cache or in your ARP cache. Well, that's why you would basically only remember the ones you're talking to, and the ones that you have talked to, you can forget them. Today, things have changed dramatically. You have a lot of memory in your adapters. But on the other hand, the cost of a broadcast compared to the yellow wire has changed dramatically. Broadcasting over wireless uses a lot of spectrum. You have to send much slower than for unicast. And on the overlay, it means tunneling to every other site, and that's completely crazy. So we have this model of transit. We have the model of switches forming autonomously any-to-any connectivity. And we have this model inherited from v4 and ARP, where the subnet will be all or a subset of the layer 2 broadcast domain. And typically it will be congruent, but it could also be a subset of it, but certainly not a superset of it. And this congruence of the layer 2 network and the IP abstractions of link and subnet are really limiting what you can do with it on the one hand. And on the other hand, you have to provide the broadcast capable layer 2 domain. And with radios, it's not necessarily possible. And because of that, we have to evolve not only the models that we have for links and subnet, but also the ND operations, which in the classical RFCs 48, 61, 62 depend on a broadcast to do DAD, to do lookup. And like I said, the broadcast is typically something inherited from this old domain that you have in front of you, but it's not necessarily there for wireless. So the base function for ND is to, as I said, to basically locate the mapping of I have this IP, what's the MAC? Now there's more to it, and in that ND extends ARP. You can discover your router and get information about your router. You can the router is capable of telling you, hey, don't talk to me, you can talk directly to your destination over the layer 2. And the biggest thing, as I said, is SFAAC, the capability for a node to have many addresses and form them when it likes. The problem with that is the protocol doesn't really let the routers know that when a device forms an address and when it stops using it. So the state of the router is very fuzzy. It's quite okay for classical ND when you have a cache, and anyway you deprecate the older information in your cache and you refresh it when you need it. But if you have a network where you want to know, like in our 10,000 node subnets, we want to know exactly who's where at every point of time. This fuzzy sense of who is where is very hard to use, very hard to install in the routing, etc., because you're not too sure the guy is still there, is using the address, or maybe he found an address and I don't know. So the way ND will work is basically expecting that you have a transit link or point-to-point link, which is a collapsed way of a transit where you have only two nodes. So it expects this any-to-any connectivity. And the other interesting thing for V6 there is this concept of a link local, which in reality, even if it has the form of an IPv6 address, is really a shim for the MAC address. What you can do with a link local at layer 3 maps what you could do at layer 2 with a MAC address. So even if it looks and feels and abstracts the MAC address at IP layer, it is still quite equivalent to a MAC address. The only cool thing is, because it abstracts the layer 2, if you have different layer 2s which have sensibly the same property, then you can reuse the link local and everything you build on the link local without changing any line of code. But then again, it doesn't have the usual usage of a layer 3 address. It's really a shim to the MAC. In a typical transit network, the subnet prefix that you will find in the prefix information option of the array, message, router advertisement, is advertised as onlink because the link is transit. And that really tells the nodes, when you need to talk to somebody, look him up directly through a broadcast on the link. So to enable this model, it means that effectively everybody must be on link and that you must have a broadcast domain at layer 2 that will span the whole subnet. And then you will basically resolve the MAC and forward end-to-end to any device that belongs to your subnet. So if you look at the drawing on the top left of my screen, basically what that means is the link local address can reach everybody in the subnet. That's what I mean by this local arrow. Whereas the layer 2 address over layer 1 can reach one hop. So you see well, it can reach everybody at layer 2, but you will forward the packet over one hop and then route over to the next hop, etc. Now, issues with that. The classical ND was really designed in Woodstock times, where everybody was nice and everybody was gentle. There were no attackers, everything was cool. And it has a number of opening to attacks, which can be quite dangerous. Maybe the worst one is the remote DOS attack. Basically, if somebody in the outside pings, so it can be anywhere on the internet, that's the bad side of this, pings an address on your subnet, your router will attract the ping and will look up his ND cache, and because he doesn't have an entry in the ND cache, he will have to hold the packet in the one here, and he will have to broadcast over your whole fabric, your whole wireless domain, whatever, the request. And like I said, broadcasts in modern networks are much more expensive than when it was a single wire. And so basically, by sending many pings or many packets to addresses that don't exist, and you have 2 at the power of 64 of them, the attacker can really DOS your router on the one hand and your link on the other, depending on the limitation of each. So effectively, the routers have some protection like throttling, but if you start throttling the request, a legitimate request may be throttled as well and discarded. So it's not very cool to have a protocol that will cause a broadcast that can be stimulated from the outside without any control. It's also open to impersonation attack for some people, like this green attacker you've got on my link here. The local attacker on the bottom right can claim he is anybody, send a packet sourced at any address in this subnet, and he can send an NA override, neighbor advertisement override, to attract the traffic to anybody else on the network. And ND does not defend that. Like I said earlier, and I will repeat over and over, the knowledge that you can derive from classical ND is only incomplete. You can snoop, you can look at, oh, did somebody send a DAD, or did somebody send an S or an A? And based on that, you can figure relatively well who is on your network. But this can be attacked by the green guy for the one thing, and any green guy could take over your table and say, oh, it's me now. And on the other hand, if the owner of the address has not used that address for a long time, you may have forgotten that you've seen him or something, and then you don't know he's there anymore. And if you have to route packet to him on a VXLAN overlay, you won't have a VXLAN entry for him, and you will have either to broadcast your old fabric or drop the packet. Same thing if the guy stops using the address. I mean, it doesn't tell you anything. I stopped using this address. No, it doesn't. So basically, the infrastructure, the VXLAN or the wireless, well, with IP, you will discover maybe that the association got down, but not that the IP address is not used anymore. So basically, the controller or the AP, whoever maintains a state about the IP address will keep that state. So basically, it's all defined for stateless networks and reactive lookup operation. But as soon as we build more modern network, which implies having state, then the state that we have is only partial, incomplete. And so you have a number of cases where you will lose your packets and drop your traffic because you don't know it's there. Or you might have too many states in your network and for addresses which don't exist anymore. And finally, the other problem is because the neighbor cache are not installed proactively, a number of scenarios, including the one described in the ground RFC, create situations where a newcomer, when he connects to the network, will have to wait sometimes tens of seconds to get any connectivity. And that's because when a phone shows up on the network, typically it's going to send a number of packets to the Googles of the world just to see if he has connectivity back. And guess what? When the Googles and the Amazons and the Facebooks or the Apples reply, if there is more than one packet, or maybe even on the first packet, the router will drop until he has resolved the address of the phone. So phone joins, router is not aware. Phone sends a packet. The router forwards the packet to the internet. Google, Facebook, Apple respond. Say Apple responds first. The response for Apple is hailed by the router. The router looks up the phone. Reply from Google and Facebook come in. They are dropped by the router. Now, when the router finally gets the neighbor cache, it will forward the Apple reply, but not the Google and Facebook. And the phone will think it has only partial connectivity. It won't allow the traffic. So you see, this kind of weird scenario happen because the operation in ND is reactive, as opposed to setting up first all the state that you need and then using it, which is what we do for routing, but not what ARP and ND do. So now let us match that for a little while on radios. So if you have a plain radio interface, like we use for the most piece in IoT, like 15.4, and I mean a radio where the layer 2 will not provide an emulated broadcast domain. By emulated broadcast domain, I would think of a BSS in Wi-Fi. You know the way it works in Wi-Fi? If the broadcast domain is defined by the AP. Everybody the AP can reach and is associated to that AP is in the AP broadcast domain. And so if anybody in that domain wants to broadcast, he will first send the packet to the AP, and the AP will effectively broadcast it. So the look and feel of that is that you have a broadcast domain and that you can do like Ethernet. In practice, though, the broadcast is unreliable and the IPv6 features don't operate so well on BSS. But a plain radio like a 15.4 or any other radio doesn't even have this ESS accumulation, BSS and ESS. So its broadcast domain is basically who we can reach. So if you look at this picture, we have a hub in the middle and we've got some spokes. If the hub and the spoke are in the broadcast domain of each other, they can talk. It might be that B can see A and A cannot see B. You cannot establish IP. Now, it can be that A can see B and B can see A, C can see B and B can see C. So we could do something, but it's probably not transitive. Look at my picture. In this picture, C is too far from A, right? So even if we want B and C to be in the same subnet, it's not a transitive subnet. You cannot operate ND as you're used to. Now, if you look at it, the scope of a link local address only needs to be unique between two parties talking to one another, because you don't forward packets anyway. So the link on which this link local address is defined doesn't need to go beyond a pair of nodes. So if I have an address that I'm the only one to have in the group of people that you see, then I can use that link local to talk to you and you can reply to me. Same thing, if you have a link local address and you're the only one that I know that has this link local address, then we can use it to talk together and basically define a link as being this relation. As we start doing this, we realize that the link could and should probably be different from the subnet. In our picture, we would have two links, A to B and B to C, and we would have a single subnet defined by B as the hub of this network, and B sending arrays, etc. So we realized that we want models where the link and the subnet are not congruent. And basically, there is not even a single broadcast domain for the whole thing at layer 2. So it would certainly not have to match a layer 2 broadcast domain. In the radio, the link is reflexive. I can talk to myself. It is asymmetrical. Sometimes A can talk to B, but B cannot talk to A. For instance, if there is a lot of interference near A, when B talks, A cannot hear. But when A talks, maybe B can still get it because the interference near A does not matter. If you have a good connectivity in both directions, then you can establish an IP link. And the model that we in the IoT and MANE as well as used is always point-to-point like that. Now, the second thing that you have to think of is which router provides the address. In the classical transit network, you can have many routers. Those routers could expose different prefixes, and you could build an address from any of those prefixes and use any of those routers. Well, that won't fly on radios, because if you, in my picture here, if C forms an address from A because it gets near A, then he has to use that address when talking through A, because otherwise it might not be topologically correct if A has to forward it. So you need to match the source IP to the router that gave you the prefix of that IP. And anyway, that's a rule which is now expressed in RFC for other concerns like multi-homing in RFC 8028. So basically, all the implementation, you need to change them just to match the source IP with the router that gave you that source IP. Also, since the visibility of A and C in this network can change rapidly as C moves near A and goes away, you need to rapidly identify the routers that are in range, and you need to rapidly form addresses if you want to use them as relay. So what we call DNA, detecting network attachment, must be very efficient and very quick. In the radio world, you can have 3 subnet models basically. Don't hope too much on the traditional broadcast. Don't count on it. The big broadcast transitive network that I showed you, it's just not what the radio provides you. The radio provides something like the circles that I showed. So if it's only 2 guys, then you can have you can build certainly your P2P link. So the IP abstraction for the link would be P2P, always P2P. And the subnet would match that, and you would also have a P2P subnet, and they could talk using click local, or A owns the subnet or B owns the subnet, and the other one forms from its prefix. Now, if you have more devices in your subnet, then if you have a central hub that sees everybody, then you can still do that with classical ND by expressing that the prefix is not on link. And if the prefix is not on link and the only router in my picture is a B, then the spoke will talk through B to get to anybody else. And so if basically B sends an array with prefix B column /64, and A and C form addresses B column A and B column C, then they can talk to another relaying through the hub, which is this not on link model that we have in IPv6. But then at this point we start going away from IPv4, but it's a small step. Now the bigger step is when you realize that you can have more hubs, and there is not one global hub that serves everybody, and then you need to basically relay, which is my picture on the bottom right. And this is what we call a route over mesh if you do the relaying at layer 3. And the typical protocol for doing this is RPL. When I told you that we build subnetworks with tens of thousands of devices, this is using RPL to enable the routing between those nodes. But like I said, to enable that routing, we need a very solid, reliable state about which address is where, because we will need to inject it in the routing protocol. So this is basically the model that I just described is basically what we call the multilink subnet. In this case, the ND operation will be over the IP link, which will always be peer-to-peer one hop, and you will be routing beyond that. So if you remember the picture that I showed you on the top left earlier, where an L3 hop was the whole subnet, now the L3 hop is between routers or host and routers inside the subnet, but it's not end-to-end anymore. It's the same hop as the layer 2 hop. So it's always one box to the next. And to go all the way to the end of the subnet, you will have to route. So basically, we will have a subnet routing protocol, which will route on host routes. And if you have that, then you can avoid the need of a global broadcast, which was what you would do in transit network. And that's really how you save resources and can scale. So basically, what you only, the host only need to find a router. And then the router will use some routing protocol like RPL to interconnect everybody to everybody. That's the Multilink subnet. With this, you big thing, you don't need this broadcast domain that you had before. And effectively, you can interconnect over the internet a network which operates the old way, like a transit network on the left, and a network which operates the new way on the right, using a Multilink subnet. It's just, anyway, a prefix that aggregates the whole subnet. You route to this prefix. And inside the prefix, either it's one layer 3 hop, multiple layer 2 hops on the left, or it's multiple layer 3 hops to host routes on the right. Okay, so the key function that enables this Multilink subnet, and basically with it the capability to know exactly which address is where without a broadcast, is what we call stateful address autoconfiguration. So it is dependent, if you like, of stateless address autoconfiguration, but as the name says, are supposed to be based on cache and lookups, reactive lookup. If I don't know, I will just look. Here we have to know every address before it's being used, which means that when a host forms an address, it needs to tell the router, hey, I have this address. And the router may say, somebody else already has it in my network, so you cannot use it. But it's going to be a unicast point-to-point exchange between a host and his router. And on the back end, using the routing protocols or central directory or whatever else, you can have very different variations of how you do the routing inside a subnet. The router will have to know whether this address is effectively unique, whether this device is exceeding some quota or whatever other rule that you would like to apply, and then say yes or no. And additionally, the host may be able to say, hey, Mr. Router, I don't know what the routing protocol is on the other side. I don't care really, but I want to make sure that you will handle it for me because I can't. And so that's part of the thing that you want to pass with stateful address configuration is additional interesting data that the router can use to do his job right. Typical information is a sequence counter when you move, so you know the latest location. As you know, REPL has a sequence counter when a route is advertised, so you can know when a route is stale and remove it. Well, same thing, if the node moves, the routing protocol, the distributed routing protocol cannot know what that sequence is at the other end of the network. It has to be provided by the host. Last time I told a router something, it was 100, now I move. I will say 101, so the new router can advertise me and get the packets because it's the freshest. Another thing that the routing protocols need is the capability to know how long it should retain a state. And that's basically the sort of information that only the host knows. So you realize that we need not only to have a very strong contract between the host and the router, but there are important information that the host should provide to the router to do this Multilink subnet well. So let's go see that in more details. So unmet expectation. What is it that IPv6 ND should and could be doing for us and is not doing? First thing, I said it, I need to say it again, I think. IPv6 ND, the classical one, is designed only for P2P and transit link. It is written in the spec that you will need extension for NBMA, non-broadcast multi-access, and point to multi-point type of topology, anything where you don't have this transit property and the broadcast. So wireless being symmetrical but not fully and completely non-transitive, you cannot basically expect ND to work as you would think. Second thing, ND is not wireless friendly. It's not overlay friendly. Why? Because it requires to broadcast DAD and lookups all over the fabric, all over the wireless domain, even if it's a very large wireless domain. Think about my thousands of low power IoT devices. Each time one wants to talk to his router or to anybody else, you would have a broadcast over the whole fabric. Just doesn't make sense. You want to avoid broadcast on any sort of radio, unless it's a satellite. Yes, satellite is good at broadcast. But for short range radios like Wi-Fi 15.4, the ones we use in IoT, you certainly don't want to broadcast. So there are another of mismatches. Like I told you earlier with this grand problem, and the Tokyo station use case is when you basically thousands of people go out to train at Tokyo and they want immediate connectivity. Well, V6, maybe the Wi-Fi with 11 Air has done great progress in doing that in tens of milliseconds, but then IPv6 just to do a resolution and a DAD, first a DAD and then a resolution will take above a second. Whatever Wi-Fi does, V6 basically loses all these benefits. Now, if you have a connectivity like radio, which comes and goes, there are a number of features in ND which expect full and total and permanent connectivity like DAD. If I send a DAD to form an address and the guy I'm DADing, the guy I'm looking, is just intermittently out of connection because the radio, fails a little bit, he misses the DAD, well, I will form the address and the address will be duplicated. We tried at the IETF on very large networks, and we found that 1 time out of 5, no, 4 times out of 5 actually, the DAD would fail on those large networks. So we just picked a PC, a phone, connected to the IETF infrastructure, and we would form on the PC the address that the phone has, and guess what? The phone would never detect it and never reply to the DAD, because just the phone is not listening to every damn broadcast. There are too many of them. So basically too slow, not reactive enough, using broadcast because it's lost. And for critical features like that and lookup, the loss of broadcast damages the protocol quite a bit. Now, so because of that, 6LoWPAN basically went up and defined a new operation, which is the stateful address autoconfiguration in 6LoWPAN ND. So we basically call that the address registration, and it is proactive, meaning you do it before you need the state. Just like in the routing table, you need the route before you forward. Here, same thing. But the address that is not registered to a router does not exist in the network. So if you get an attack from outside for an address which is not registered anywhere, the router will drop the packet. It will not broadcast a lookup. The way it's done is RFC 8505, which provides the extended address registration option. The address registration option was initially defined in RFC 6775, but 8505 is a quote-unquote a correction of it. So it kind of inherits and fixes 6775. So the extended address registration option in particular provides this sequence counter that I talked about, which can be injected in repo and used to find which is the most recent location of a device and make sure that the route that repo selects is the one that goes to this most recent location. There is there are more information in this message, in this address registration option. One of them is lifetime. Then again, that lifetime can be directly fed into the routing protocol to maintain the route for the lifetime of an address. So the host comes in, finds a router, autoconfs an address, but then it has to register it. So it's an NS, I will show you that. The router likes it, it will say NA, I'm very happy with it. And what differentiates this NS-NA is the presence of this extended address registration option. So with this, the router knows how long lifetime the host expects to use this address. It will know if there was a movement, the sequence of this particular move by the device. And there is a unique ID which allows to do that basically inside the network. So if all the routers have a way to find all the registrations, for instance, it can be shared by BGP, or it can be done at the root of a REPL network, or there can be a 6LBR, which is a total registry. Typically, we put it at the REPL root because this is the same table. Basically, you can check that the address is unique and reply to registration, yes or no. So the registration exposes the IP address, it exposes the mapping with the MAC address, and it exposes the location of the address, which is the router where the address is being registered. And if the host setting a bit called OR, if the host claims, hey, I can't do my routing, please do it for me, then effectively, based on that solid state that the router has, it can do the routing protocol like the REPL. Now, the second piece that's important and quite different from ND is the way we prove that an address is effectively owned by the guy who uses it or claims it. We have this other RFC 8928, where when you register an address, you will also register as a unique ID a cryptographic token, which derives from a public key. So you autoconf an address, but you also autoconf a public key. It's not a PKI or anything. You just autoconf the key pair like you would do for SSH with keygem. And the cool thing is, because we have this total registration of every address, we can not only store the address, but we can store meta information with this address, in particular, this cryptographic token, which means that if somebody wants to use this address as source somewhere else, but has not proven that he uses the private key, we can drop his traffic. If somebody somewhere else in the network claims this address using an NS, we can refuse if he cannot prove that he is the owner of the address through the private key again. So 8928 basically provides this exchange, this challenge phase, where when a node comes in with 8505, and claims an address, we can challenge him for ownership. So it's really first come, first serve, meaning that the first come will say, I'm forming this address. Network will say, oh, it does not exist, so it's yours. Give me your cryptographic token. Okay, I will store it. So now if somebody comes in for that address, I will check if he has the private key. So the stateful operation basically can be described as this. First, it's a proactive operation. You register all your addresses, all of them, before you start using them. The first one you register is the link local. The link local knowledge stays within this host and this router. Like I said, it's only important within this link, and this link is the P2P relation always. So if the router hasn't seen this link local that you want to use ever, it will just say, yes, I registered it for you. The registration stays local to this router. You can register the same or a different link local to another router over the same radio. Once you have this establish this relationship, link local relationship between the router and yourself, now you can expose your global addresses or your unique local addresses through registration. And that's when there will be a backend operation between the router and the rest of the world to check that this address that you want to claim is unique, whether it's already owned by somebody else, etc., etc. And that's what the NSNA with the arrow will do for you. Now, the router impersonates an abstract global registry. If you use EVPN, then it's going to be whatever you learn through BGP. If it's connecting to an Ethernet backbone doing ND proxy, then on the backbone it will, if you do a lookup, it will do it on the backbone if it doesn't have the answer. If you do that, same thing, it will that on the backbone and come back to you if there is duplicate. So it's completely abstract. The NSNA to the router is completely abstract to what happens on the other side of the router. And the one I will, depending on how much time I have, but my intent is to show you at least the case of RPL. You'll see how 6LoWPAN ND is effectively redistributed into RPL. But the cool thing, it's completely abstract. So it can be redistributed in RPL, but it can be redistributed in Rift, in ND proxy, in EVPN, in any technology, you know, that you can have on the back end. Now, you don't need that anymore using a broadcast because you have the state of every address. Part of the arrow is this registration ownership verifier, which is what replaces the unique ID and contains the public key in some form. And that's using that cryptographic token as unique ID. You can verify when a new registration comes in, whether it comes from the same token or not. If it's a different token, then it's a different node, it's a DAD. If it's the same, then you can challenge him for the ownership of the private key. And then it's just a movement. For forwarding, you don't need lookup anymore. Why? Because you just pass the packet to the routers and then the routers do their routing. So all the broadcasts which were caused by NS lookup are gone. So the ARP model is completely gone. No more ARP model. Everything's through the router. You could imagine to do a redirect if the router knows that two hosts are connected on the same interface. But it has also to know that the interface is transitive and very, very stable. Otherwise, he will just prefer to forward the packet himself. So when the node moves away, the routing is not broken. And finally, address families. Right now, we have defined 545 only for IPv6 unicast. We have the draft on the works for IPv6 anycast and multicast and how that's redistributed into RPL. For v4, we have not done it at all. If requests come in, then we'll do it for v4. But basically, v4 networks today, they really are like I showed in my first slide, this transit network. And right now, we don't see them extending beyond that kind of model. So we have just not done 545 for v4, but we could, easy. So I said it, let me go into more detail now. the cool thing about this registration, it is an abstract interface to routing, to RPL, to ND proxy, to whatever. If, for instance, you have a RPL network and know that advertises an address already injects it in RPL, it will not set this error flag that I mentioned. Because he wants his parents in RPL to know he has this address, but he's big enough to tell the root about it, or to do the DAO for them in RPL. So he participates to RPL, he's a RPL aware node, he will not set the error flag. On the other hand, if the host doesn't know, doesn't care, doesn't have the power, the memory, the support of whatever routing is in the visited network, then he will just set the error flag. I don't know what you do in the visited network. I want to make sure that you will do what the necessary to give me connectivity back. And if the connectivity is RPL, then the router will do RPL. If the connectivity is EVPN, he will do EVPN. If it's Lisp, he will do Lisp, whatever. For the mobility inside the fabric, since you need to inject route, you need to know if the route you want to inject is the freshest one, critical thing. It's something that we know very well from the first days of the MANET mobile ad hoc networking protocols. You have to have a sequence when you inject something, a route at a new place. Because as the guy moves and moves and moves, the route that counts is the most recent one, the freshest one. And only the node knows, where it is and what's the freshest. So it's very good that the node actually provides this sequence counter. So we provide trust because of the proof of ownership of RFC 89228, and we avoid duplicates when it's not Anycast, because we basically compare this unique ID, which is actually the proof of ownership itself. Usually can also be your MAC address. And then again, critical thing, you don't look up, never. You know your router, you give him all your traffic, and you expect your router to give you your traffic back. But you can register to more than one router, and then all of them will inject the route in the routing fabric, and the shortest path will win, or equal cost multipath, either way. So basically, the summary of this, we started with 6775 and updated it with 8505, which is the new way of doing the registration. It's partly incompatible. Some of the things that were in 6775 don't work anymore. For instance, the way you set the TLLA and the SLLA option, which give you the MAC. So it's being reversed, so you really need to know what you implement. Anyway, the protocols allow you to discover that, so you know what you're talking to, and there is a backward compatibility discussion in 8505. And more importantly, the model for link local is this point-to-point thing. We failed to describe it enough in 6775. Now we say, hey, the scope of your link local is really you and the guy you're talking to. And virtually, if you talk to somebody else, you could use the same value, but it's a different scope. It's like a different link. At the IP layer, it is a different link. And so also, we have this error bit, which was not present. We have the TID, which was not present. Basically, 8505 allows you to redistribute in the routing, which 6775 could not really do. So with 6775, you could have a node which was fixed, attached to another one, but it could not move over the fabric or over the mesh. So we've got 8928, which basically secures the registration. And we've got 8929, which is how you do proxy. So if the nodes are, for instance, Wi-Fi nodes, and they use the 8505 to register to the AP, and the AP now is a layer 3 access point, then the AP can do ND proxy over the wire on behalf of the devices, and that's how you will do it. On the works, we have 2 RFCs and soon more, I guess. But the biggest one is this 6LoW multicast registration. It updates both 6LoWPAN ND and RPL to enable the registration of Anycast and multicast address. And so you don't need to run MLD at all in your IoT network anymore. So basically, you register with exact same code, pretty much same code, your multicast addresses as you do with your unicast, and RPL will transport that as multicast. On our way, we are defining a new non-storing mode multicast operation, which did not exist before. And then the 6LoW unicast lookup is more like we're porting this model onto the backbone, onto an Ethernet backbone. And we want to avoid the broadcast. It's pretty cool, for instance, if you have a distributed fabric. So we say the 6LBR, which is the abstraction of the central registry, which has everything, can be a server somewhere, like Lisp or whatever. And then you can look him up before you do a broadcast. And with this, you save a lot of your broadcast. It's pretty much what we do already for IVPN. Well, considering that the whole registry is the BGP infrastructure. Now, let's look a little bit at the flows for this. So the error option is what we have. So you have a number of bits, and the most interesting one is the R bit, which says redistribute in the routing. The T bit basically says that the TID is set, and that's how you know that you're talking 8505 as opposed to 6775. 6775, the flags are reserved, the TID field was 0. So if the T flag is set, you know you're at 505. Then you've got the lifetime. And this rover thing, which in 6775 was a unique ID based on MAC, so it was UI64. Now you've got a real rover, which could have variable size. And basically, it's an operation based on your public key that you can do again. So you can, but when you have a public key, you derive this thing, and that's what you announce. Okay, and Savvy is basically the idea that somebody uses an address, we should be able to say is really the owner. I mentioned that we can prevent, the router can basically check if it has a registration for an address before it will forward the traffic coming from that address. So if there is this guy coming in and he wants to source traffic with an address that he has not registered, then the router can drop it. With typical ND, that was not the case. So we basically prevent hijacking, somebody impersonating sourcing traffic with an address, and somebody sending an NS claiming an address. So here is basically the flow of 8928. So what happens is, as in 8505 in general, the 6LN, the node, the host, which wants to claim a new address, will send an NS with this error option, and he will derive a cryptographic ID from his public key and put it in this rover field in the error. Now, because the network already knows that it is a cryptographic registration somewhere else, or because it's new but there is a bit says it's crypto, the 6LR will check, and that's new with 8928, will check that the guy effectively has the right credentials for this cryptographic ID. So the first time, it's really a check to make sure that the way we compute it is compatible with the host. When it's a movement and the host shows up somewhere else, it's because the 6LBR on the top right remembered the crypto ID that was registered to another 6LR, and there will be a check. So anyway, so the 6LN is typically challenged. The 6LR validates that the cryptographic ID matches the private key that the 6LN has. And with that, there is this direct exchange to a 6LBR, which is an abstract thing. It's not in the host to router interface. It abstracts what goes in the backend. Could be the routing protocol, could be effectively that message, could be Lisp. And what comes back as a status of 0 if the registration is by the same guy, same cryptographic ID, and it is or did not exist in the past, in which case the 6LBR will create the entry. So application of that, and that's when I said I will show you what happens to REPL. Now, if you don't know the slide where you will find other cases like EVPN, etc., and backbone router for the proxy. But in the interest of time, I just decided that I would present you the REPL case. So RFC 9010 details the relationship between a node which is not aware of REPL and the REPL infrastructure, and basically how the router, which is REPL aware, will advertise the external route to this external device, which is not RPL aware. And the RPL unaware leaf, so it's a host attached to a RPL router, can use 6LoWPAN ND 8505 to register his address and ask the router to send that address in RPL. And the 6LR will generate a DAO on behalf of the RPL unaware leaf. RFC, and there is this external bit, E bit, which says external, by the way, and that bit was prepared in 6550 in RPL just for that. So we finally, with 9010, with 9010, we finally did something that we prepared way in advance. The RFC 9008 provides all the encapsulation rules for RPL. And you will see that if it's an external node, you can't even know for sure that it will support tunneling. It's not completely a must in a host. So when we do tunnel in RPL, we always tunnel to the router. And when we represent an external route, we always use non-storing mode DAO. Even if the RPL is using storing mode, that's the storing mode is just for RPL aware nodes. For RPL unaware nodes, they will be advertised to the root using non-storing, which will enable the root to tunnel to the 6LR, which is serving this RPL unaware leaf. So the way the RPL root knows where to tunnel to is because we are using non-storing mode always for external routes, and that's specified in 9008. Again, in preparation for 9010 and all the other routing protocol, all the other ways you could have to derive an external route. For instance, if in the future you redistribute a protocol into RPL, and that protocol has routes to addresses which now are external, they will also need to be tunneled to the 6LR which connects that. And so they will be advertised as external, and you will need to use an extension of, well, non-storing mode really, but for a prefix to advertise them and get them the tunnel to the 6LR that connects the two networks. And like I said earlier, we are extending for unaware leaf to multicast registration and anycast. And for this, we have a new mode of operation that enables a multicast in a non-storing mode. And the way we do that is by ingress replication, meaning that the root will copy all the 6LR that have at least one registration for a multicast address. And it will tunnel to one of the 6LR that have a registration for an anycast address. So we basically, in the registration, signal anycast and multicast with new flags, and those are now propagated in the DAO. So the RPL knows, oh, it's the RPL root knows it is a multicast or an anycast address. So the flow goes like this. This an SRO from this RPL unaware leaf on the bottom right, 56. So he registers his address and he has the R bit saying, hey, I need you to give me a routing back. And here is my sequence, because maybe I moved, but now I'm this sequence. And based on that, router 46, which belongs to the RPL fabric, will send in non-storing mode. It will send, I told you it's always non-storing mode for external routes. It will send this DAO saying, hey, I'm the transit 46, the target is 56, here is the sequence. If it's the most recent sequence, then the root will always turn on to 46. 46 will decapsulate and deliver. So let's see how that goes. First, the root acknowledges that if it was requested, and here it's always requested. And when the acknowledgement comes back, then the 6LR 46 sends an NA arrow with the R bit set saying, hey, I have injected your route into RPL, so you can trust me to provide you return reachability. Then when the packet comes in from the internet, and even from the local domain, actually, it's always the same. Since the route is injected using non-storing, nobody knows the route to 56 inside the network. Only the root knows. So it operates like in all non-storing, meaning that the packets from the inside of the DODAG or from the outside of the DODAG, they all end up at the root anyway. using the default route inside the geodag and using the route that the root has advertised is external. And with this, the root needs to tunnel the packet, and that's what you see basically on the right. The original packet X to 56 goes encapsulated, and since it's non-storing, it's going to be the list of hops in the routing header, which says basically via 13, 24, and 35. And the way it's represented now is when it arrives at 46. So basically 35 forwarded the packet that you have on the top, on the bottom right, to destination 46. And you can see in the consume routing header the steps that were made. And 46 decapsulates and delivers the original packet to 56. So 56 is completely unaware that there was RPL in the middle. When the node sends a packet over the RPL fabric, same thing, 46 will have to encapsulate to add what we call the RPI. I explained that on the previous session. So same thing as for non-storing mode, but it's just that the encapsulation is done by 46 as opposed to the originating node when it's RPL aware. So 46 encapsulates, adds the RPI, and forwards to RPL. We have an opaque field in the registration that 56 can use to indicate which RPL instance. If 56 cannot do RPL but can pass information to the RPL network. So there is a way to signal, hey, I'm using this opaque to pass your instance ID. So if 46 belongs to more than one instance, it can select the instance ID. And all the other slides that I have now, think of them as for your own consumption. And so you see I have Wi-Fi, backbone router, I have a number of things, EVPN as well. And I have no time to go through them, but I hope you like reading them. So key takeaway, IoT has moved to always P2P IP link model and multilink subnet model. So the link is not congruent to the subnet, and none of them is congruent to the layer 2 network. You can use this model on wires and wireless. It's not limited to wireless. It allows you to decouple the broadcast domain at layer 2 with what you want to use as your IP subnet and your IP links. If you start doing this, you save the broadcast. Your routing and forwarding are a lot more efficient. This in the IoT world, this is called route over, and typically we use RPL for that. For instance, 60 uses RPL for that. That's the same thing that you would do in a DC overlay using, for instance, VXLAN, right? You tunnel to the last router, and then the last router decapsulates and delivers to the RPL unaware leaf. So effectively, this is a model. This is very generic. So you can use this model to register to the first hop router, and if you want to do VXLAN, you will do VXLAN. So yeah, I mean, how far do we want to regionalize it? We would like to generalize it to any L2 network, including EVPN fabrics and stuff. So that's why we have all those drafts and all those flows. And with this, I will be ready for questions.
Great. Thank you so much, Pascal. Yeah, so if you guys have questions, please go ahead and raise your hand and I can unmute you, or else, go ahead and type it into the chat window and I'll read it to Pascal. And while we're waiting, I have one for you, which is, I'm really glad you said that about the last stuff about generalizable to other networks too, because I was curious about that. The reason being is I was just doing some testing on my own Windows machine, and it looks like a privacy address is being generated every 7 minutes, and that appears to be the default. I've not set that. The cut a long story short there, that's a ton of addresses that are potentially clogging up my neighbor cache. And I'll say the other thing is that I don't know if you guys get involved with PCI, the payment card industry standards, because apparently in payment card industry standards, they suggest or recommend IPv6 privacy addressing, which then leads back to the problem that I'm talking about, and then back to neighbor discovery. So just will be interested in your comments on this whole arena. Yeah. Pascal, can you hear me?
Yeah, sorry, Nalini. I had muted on my side. I'm sorry. I was saying, if you can find me somebody who's willing to implement it 505 on any of the big stacks, Windows, Apple, Linux, I'm fully interested. Because, yeah, the key thing you mentioned, the nodes will renew addresses aggressively, more and more aggressively. And initially, when they started renewing addresses, some fabrics failed because we have to maintain state for each address. To do overlays, to do wireless associations, to do, in our controllers, we know which addresses there are in our switches, we maintain state, and we do that to protect the devices against impersonation attack, etc. And we do that based on snooping. And now if you need to inject that address in a Lisp registrar, MSMR, or in EVPN, well, the more addresses show up, the more state you have to have in your network. It's not, you say, clogging my ND cache, but your ND cache is nothing compared to an EVPN fabric that is distributed in multiple sites across the world, right? So the need is immense. Now the problem is they will renew this address, but they won't tell you, oh, I just renewed it. You might snoop ND if they send an override, but it's discouraged. And you may see the DAD if you're lucky. And they will never tell you when they stop using it. If they use it for 7 minutes, the routing fabric doesn't know. So your EVPN fabric, your Lisp fabric, your IPs, whatever maintains the state for that address, will keep that address for a long, long time. So it's very inefficient. And the other side of that coin is if the fabric wants to avoid too many broadcasts, what they call broadcast, unknown, and multicast, BUM. All those BUM messages cause broadcasts at the fabric level. If you don't want those broadcasts, you don't do them. That means that a node that you forgot or you've not seen will be unreachable. Think about that printer on the corner, which has not been used for days. If your router has rebooted or anything, nobody remembers he was there. Or if you assign a lifetime to him without any knowledge of what the real lifetime should be, if you think it should be 7 minutes, but actually this guy is sleeping for weeks in a row, then you completely forget about him. And now somebody wants to send a print to that printer. And guess what? He has the IP address, but your fabric doesn't know how to get there anymore. So it's critical when you have a modern network, whether it's Wi-Fi, whether it's overlays, to know exactly who is where. So you can do the mobility right, so you can have the right state in your overlay. And so the need for 8505 is huge. It's just that it is a routing problem for the most piece. The stacks don't really care. They expect the routers and the switches to do the right thing. And they expect to be able to press any damn address on the network at any damn speed. And the network should always do its piece. That was probably right in the times where ND, traditional ND was acceptable. But it's not acceptable over our fabrics. It's very, very bad over a big wireless. We measured the NS broadcast during a keynote at a very large conference. There was 300 per second. So and knowing that the Wi-Fi has to send it at the minimum 5 speed because you have to broadcast them and reach everybody. So you want to use a 5 speed that everybody can listen to, even the guys which are far, far away. That means, you know, you're clogging the bandwidth. Each broadcast clogs the bandwidth for potentially the time of 100 unicasts. So the cost is huge, completely huge. So we have all sorts of tricks now, IPs and fabrics, at least at Cisco, I know them because I contributed to writing them. But the native protocols are completely broken. If we didn't do all sorts of tricks, then it would already have failed. We do those tricks so we keep the protocol alive longer than they should be. But yes, we need 8505. Any help, much appreciated. On the Cisco side, you're ready to deliver it in the routers and switches, but we need the main stack to come with an implementation, otherwise it just doesn't make sense.
No, so, oh my God, Pascal, let's talk offline, because what we can probably do, and we'll get together, there's one of the folks that we work with, you know, I mean, one of the great things, of course, is having, you know, so much participation from India and IETF. Let's see if we can, at a minimum, get it implemented inside the Linux kernel. And because we can
fabulous.
Let's talk offline, because we can do that. You and I can let's start a project. I'll start that discussion, and then I have some things that I need to talk to Microsoft about. So I can start that particular conversation, but that's going to take, of course, longer. And yeah, I'll start. Go ahead.
Anything is good. I mean, all the help, you know, basically to reach out to the major stacks is great. We have proven it works. We have thousands and thousands of devices in single subnets using low power links because we got rid of broadcast. That's as simple as that. And the route works. The routes work because the state we inject in the routing is only addresses which do exist. And we have the latest location of those addresses. So if you use 8505, not only can you say, I want to use this address, please install a routing state for me, but you can also say, I will use it for 7 minutes or 10 minutes. And you can also say, I'm renewing it because finally I'm going to use it for longer. So let's renew it for an hour. And then you think, hey, maybe, oh, I'm stopping it. It's done. You re-register it again with a lifetime of 0. So you have a tight control of what you tell and negotiate with the routers. And for the lifetime that the router agrees upon, you will get your packets, even if you go to sleep. And remember, we want to make the internet green, which means we want to be able to say, hey, I'm off the network for a little bit because my processor is sleeping, my radio is sleeping, whatever. Well, if you do traditional ND, you can't sleep. ND does not let you do that. Because if there is a dad while you sleep, the guy takes your address. With our stuff, the router will make sure that you're the owner and it will have a state. And if somebody else comes in, even if you sleep, it will protect you.
So this is, okay, so my perspective too is that the people that we work with have very large and they want to have very controlled networks because, I mean, if you think about like
exactly. Corporate network.
Yeah. If you think in like New York Stock Exchange, yes, we want to know exactly.
Any data center, you want to know who's where at which point. And if you use VMs and you can move those VMs, you want to advertise the route to the server that has the VM at this point of time and not an old one.
No, and so there's a huge amount of stuff that I really, really like in what you're doing. And so let me start that conversation offline because, as I say, one of the things that we're looking at too, as I say, it all kind of this. I really wish you were going to be at the IETF because then we could just sit down over,
I'm so
adult.
Sorry. We have this constraint, and I'm sad to say it's budget constraint. But I'm not flying this time. So, but happy to discuss with you and start a project and everything because, it's late. Yeah. It's probably because the hosts themselves don't feel the need. It's mostly a need for the routing infrastructure. But if they want to be served well, they need to do it.
Our enterprises need it because as I go through and start looking at this, I'm like, Jesus, I'm recommending IPv6 to all these people, and they're going to run into problem 1, problem 2, problem 3, and I'm like, oh my God, and and so, but I think a lot of the host vendors, when they hear from the end user customer, but see, end user customer doesn't know yet. And so, but I'll tell them, what the problem is, so let's work together. This is so exciting, Pascal.
Please look at the slides on EVPN and I can forward more slides.
Okay.
No, actually, I'm missing slides I wanted to put in that slide so maybe they are deeper after the question. So yes, you have more details about the issues on classical ND after the questions. If you look at that, I'm detailing all the issues that I have discussed one by one, explaining what they are. And can I do a wireless? I have a lot more slides as usual than I could present in 1 hour. So
no, this is great. This is great. Let's go one step at a time. Start the conversation. Let's get it implemented in Linux, because there's a lot of stuff you guys are doing that I would like to reuse actually in our encryption of IPv6 extension headers. That's a whole different conversation, because I really like that address, the token. That cryptographic token is sweet. You know, if we can read the token.
And you know what? In my EVP, there is a draft called secured registration or something, a draft at BESS, B-E-S-S, where we do EVPN under my name. And you will find that we redistribute that token into the EVPN fabric. So if an address shows at another place with a different token, we can reject it. And basically, this is giving you zero trust. Because today, if you have 1x access to a network, you can do whatever shit you want. If you want to advertise packets with any MAC address, you just send packets, source them with that MAC address. EVPN will happily give you all the traffic to that MAC address without a check. Right? And so what we have done here at layer 3 for IPv6, we should really be doing at layer 2 for MAC, at layer 3 for V4, and at layer 3 for V6. Because otherwise you don't have trust.
No, I completely agree. And also the other thing, which we haven't even gotten into, is we're getting, I know we're getting over time, but the power consumption. I mean, these days, we really have to thinking green, even in the data center. You know what I'm saying?
Yeah, I'm with you. I mean, it works. I mean, today on wires with power, the industrial guys tell us, rule of thumb, 100 devices in your control network. Because after that, the control network starts fluctuating and your control loops has trouble. 100 devices on Ethernet, right? Because of, well, whether it's V4 and V6, because of the broadcast utilization. And guess what? V6 is a lot worse. Because you have more than one address and you renew them continuously. So the broadcast, and you do that and you do lookup. So it's not only lookup. So because of that, there is a lot more broadcast with V6 than V4. And V4 already stalls at around 100. But it's a really critical usage, right? Control network has harsh requirements. But basically, they know that beyond 100, they fail. And guess what? We built subnets of thousands of nodes over links which are 256 kbps and lose a lot of packets. And yes, in terms of power, I mean, imagine, scaling to that level with wires, what kind of power that would mean. And it's just because they do all this broadcast thing. That's really what's killing everything. You've known that from the V4 times. I mean, what they call the broadcast domain and broadcast storms. And this is the thing that's killing everything. And the other thing I did not mention is the loops, right? If you're at layer 3, you have a loop, you have a TTL. But when you have a layer 2 loop, wow, it hurts. We call it a meltdown.
No, this is just crazy. This is crazy. Okay. All right, guys, we're getting way over time. Guys, if anybody has questions, afterwards, please let me know. I hope you guys are all hearing the audio. I did get one person who said they weren't hearing audio. So I hope you guys are all fine, because I'm certainly hearing it. And then we are, we're recording, of course. But thank you so much, Pascal. I will contact you offline. And if any of the rest of you guys, if anybody who's still, crazy enough to be still on and listening to all this, if you guys want to keep track, and if you want to, keep track of this, or maybe, help test, like when we get the new Linux implementation, because we really need this in classical ND. This kind of stuff. And if you guys want to help test or anything like that, or work together, do let me know, and we'll put you to work. So we have added.
If somebody works for a Samsung or a Apple of this world, and would help, spread the good news to their own company and start, considering implementation. That's also good.
Oh, wonderful, perfect. That's yeah. We'll certainly I'll talk when at the IETF. We'll certainly pull Apple and Microsoft aside. We'll let them know that we're working on that, and then ideally, as I say, because I think a lot of times if you have a reference implementation, and that's what I'm saying. It's like if we have
Linux, I mean, I have better hope that Android would follow suit or something. I know Lorenzo is not very keen on that because he really likes the model where I can claim any address and it's always the router's fault. But at some point, there are issues which have been advertised tons of times on the networks, like Android will not connect to an enterprise network because enterprises don't want the host to form any address he wants, so SLAAC is barred. And the only thing that today enterprise can do is the HCP. If Android just has SLAAC, so basically on V6 you don't do anything in an enterprise network, and you have V4, and basically that's where we are. We've been for years. Now with this model, you can still auto-configure address, so it's in the middle. I know it's a hard trade-off for those who really want to do SLAAC, but at least it's a trade-off that can be accepted by the enterprise.
Well, 100%, because that is a real need. And if you give the option, I mean, say if you want, you can do stateful auto configuration. If you want, you can do stateless. And then, because if you give the end user, I mean, the network administrator the option, that should be okay, I think. But I think this really helps solve a lot of problems that I can see coming for classical ND and our enterprise network.
Yeah, exactly. I mean, we all see them coming. It's just I can't believe that the stack don't implement. Maybe we should. The problem is when we first introduced this to 6man almost 10 years ago, they were not receptive, and Lorenzo bought really. Because he really wants his SLAAC thing. He doesn't want the router to be able to say no. And when you have a managed infrastructure, the managers of that infrastructure, corporate data center, whatever, they want to be able to control what's going on. They want to be able to say yes or no. And so that's basically the basic philosophical discussion here.
No, absolutely. And I think now we have more enterprises involved. And so I think that's where, a group like this, INTC, which is a nonprofit, and there's a lot of enterprises involved. And also, I worked with there's a bunch of people that I'm working with that are very, very large, and I think they will have all these different.
I mean, that would be lovely, Nalini. If you can start this, I'm well paid for my time today by just having this sort of outcome. That's wonderful.
well, thank you so much, Pascal. Let me let everybody go, guys. We've added one more, which is we're going to be doing some. Rahul is going to be reading traces with us, which I am very much looking forward to for next time. And I hope we can add a couple more to this. And then ideally this time in 6 months we'll have a reference implementation of classical ND with some of these wonderful features. So thank you all so much, and thank you, of course, Pascal, most of all, for your time. Okay, thanks everybody.
Bye-bye.